Okay, so take a look at this curve. I mean, it's not your standard function, right? It loops, it crosses over itself. It basically defies all the simple rules we're used to. So the big question is, how on earth do we apply calculus to something this weird? Let's dive in and find out. So we're going to start this whole thing off not with some dry formula, but with a puzzle, a visual mystery really, in the shape of this very peculiar curve. And our mission, if you choose to accept it, is to use our calculus toolkit to figure out exactly what's going on here. All right, here are the culprits. These are the parametric equations that are drawing our curve. Now, the best way to think about t is as time. So as time ticks along, a point is moving, and it's tracing out this path. Its x-coordinate is just t squared, and its y-coordinate is t cubed minus 3t. Now, here's where it gets interesting. When you actually plot this out, you don't get a nice, simple parabola or a straight line. No way. You get this wild shape with a loop. It actually crosses over itself. And what that means is that it hits the very same physical point at two different moments in time. You can also see spots where it looks like it goes completely vertical and other spots where it flattens out. And this, right here, is our central question. I mean, think about it. If the curve is at the same point twice, does it have one slope there, or does it have two? How can we even begin to describe its steepness at any given moment? This is the puzzle we are here to solve. So, to crack this puzzle, we're going to need the right tools. And luckily for us, calculus provides an absolutely killer toolkit just for parametric curves. So let's open it up and see what's inside. And here it is, the key to the whole thing. This is our formula. The slope, dy dx, is just the derivative of y with respect to time divided by the derivative of x with respect to time. Now, why does this work? Well, it's really just the chain rule in a clever disguise. See, since y isn't a direct function of x, we have to analyze how they both change with respect to our parameter, t. You know, here's a fantastic way to think about this formula, and I really love this. Don't just see a fraction of derivatives, see a ratio of speeds. The slope, at any instant, is literally just how fast the curve is moving up or down divided by how fast it's moving left or right. This gives us this incredible, intuitive grasp of what's actually happening. All right, we've got our toolkit, we've got our intuition, it's time to get to work. We're moving from the abstract theory to a hands-on investigation of that crazy curve we started with. Okay, our first target is that self-intersection point. We know what happens at the coordinates 3, 0. The challenge is to prove, mathematically, that the curve has not one, but two totally distinct tangent lines at this single point. So here's our game plan. We're going to tackle this step by step. First, we'll find the two different times, the t values, that the curve actually arrives at the point 3, 0. Then we'll calculate our speeds, dx over dt and dy over dt. With those, we can compute the slope for each of those times. And finally, write out the equations for our two tangent lines. Let's do it. Okay, step 1. We set our x equation to 3 and our y equation to 0. The x equation, t squared equals 3, gives us t equals plus or minus the square root of 3. Pretty simple. The y equation, t cubed minus 3t equals 0, gives us t equals 0 or plus or minus root 3. So what are the times that satisfy both equations? It's t equals positive root 3 and t equals negative root 3. And there's our proof. The curve is at the exact same spot at two totally different times. And now for the big payoff. We take these two t values and we plug them into our slope formula. At t equals positive root 3, the slope is positive root 3. And at t equals negative root 3, the slope is negative root 3. So we have two different times leading to two different slopes, which gives us two completely different tangent lines. This shows exactly how the curve can pass through the same point but be heading in totally different directions. So we've figured out the intersection. But what about those flat and vertical spots we saw earlier? Well, let's go back to our speed analogy. A horizontal tangent is just a moment when the vertical speed, dy over dt, is 0. The curve just isn't moving up or down at that instant. And a vertical tangent, that's when the horizontal speed, dx over dt, is 0. All the motion is purely up or down. And finding these points is easy now. We just solve for those conditions. We set dy by dt to 0, and we find the curve is horizontal when t is plus or minus 1. That corresponds to the points 1, negative 2 and 1, 2. Then we set dx by dt to 0, and we find it's vertical when t is 0, which happens right at the origin, 0, 0. Just like that, we've mapped out all the critical points of the curve's slope. But, slope is only half the story. To really, truly understand the curve's shape, we need to know how it bends. Is it curving upwards, kind of like a cup, or is it curving downwards, like a frown? This, of course, is the idea of concavity. So, here's the next logical question, right? How do we measure the rate of change of the slope itself? This is exactly what concavity is all about, and to figure it out, we've got to take things to the next level. We need the second derivative. Now, I know this formula can look a little intimidating, but the logic behind it is perfectly sound. We want the rate of change of the slope. Our slope formula is in terms of t, so the first thing we do is take its derivative with respect to t. Then, and listen up because this is a super common trip-up point in calculus class, we have to divide by dx dt one more time to get the rate of change with respect to x. Okay, let's break it down. First things first, we need to find the derivative of our slope function, that dy over dx we found earlier, with respect to t. This means we have to use the quotient rule. And after you work through all the algebra, the numerator of our second derivative formula simplifies down to this nice expression right here. And now for the final step. We take that result from the previous slide and we divide it by dx dt, which, if you remember, was just 2t. And boom, that gives us our complete final formula for the concavity of our curve. Everything we need to know about how this curve bends is captured right in that one expression. So how do we actually use this thing? Well, it's all about the sign. It's that simple. When the second derivative is positive, the curve bends upwards. For our formula, the numerator is always positive. So this happens whenever t is positive. So for the entire journey after time 0, our curve is concave up. And you guessed it, when the second derivative is negative, it bends downward. This happens whenever t is negative. This one little formula tells us the entire bending story of the curve. So, there we have it. By applying our calculus toolkit, piece by piece, we've taken this bizarre self-intersecting curve and we have completely, totally described its behavior. The puzzle is officially solved. So, here are the essential tools you should really take away from all this. You now have a complete method to find the slope, locate all the key points, figure out the concavity, and even analyze those complex intersections for pretty much any parametric curve you'll encounter. This is your fundamental toolkit. And the best part is, this isn't just for one weird problem. These exact same principles can be used to analyze the motion of a point on a rolling wheel, which creates a beautiful curve called a cycloid, or even to describe the path of a projectile in physics. This method is incredibly versatile. So we'll end with this thought. You've just been handed a very powerful set of keys. The world is absolutely full of complex curves, describing everything from planetary orbits to the paths of tiny particles in a magnetic field. So the only question left is, what will you choose to unlock next?